Good evening, ladies and gentlemen. This evening we're going to be looking at organic chemistry reactions. In a previous lesson, I've already looked at organic chemistry conceptually. So we've already looked at what a homologous series is, what a functional group is, and a little bit about how they fit together. So we've already done all of that in a previous lesson. Please, if you haven't yet watched it, make sure that you go back and you catch that one as well. Because today what I'm going to be focusing on is jumping straight into the types of reactions, and we'll hopefully get you to the point where on Thursday we can go over some exam questions. I am going to try and incorporate some practical activities as we go through this, so it's not just going to be me telling you things, but I'm going to do questions where I say, we start with this, we do this, and you've got to tell me what you think the answer might be. All right. So let me just quickly make sure everybody is muted. Please, can I ask you to make sure that you remain muted? I've done it so that everybody starts off muted, and you've got to physically unmute yourself, which you're welcome to do if you have a question. But otherwise, if it's just for background noise, it gets a bit frustrating. All right, so let us get started. Okay, so I'm going to be discussing a range of different reactions tonight. But I'm going to get started with the overview that we are doing organic chemistry reactions. And we're going to start with one kind at a time. So the first thing that you need to understand with organic chemistry reactions is that overall we can define almost all types of organic chemistry reactions under three groups. We could say that we either have an addition reaction, a substitution reaction, or an elimination. I find it useful to do this overview before we look at the different specific kinds, because looking at what the difference is between addition, substitution, and elimination helps to make life a lot easier later on when you're not 100% certain which of the ones you're looking at. So very importantly for me, in an addition reaction, we start with a double bond, and at the end of it, we've only got a single bond. So I often describe with addition reactions that the bond order decreases. Now, many of you have never heard the term bond order, but when I talk about bond order, this is a double bond, and it is a higher bond order than a single bond. So we go from a double bond to a single bond. Just give me a second. Okay. If we talk about a substitution, basically with the substitution, you will start with one group on a carbon and you will replace it with another group. Now, I know that I've technically left off everything else that's happening on these carbons. That is irrelevant at this point. It's just that we go from a double to a single, or that we go from having one substituent to having another one. So realistically here, there are five other bonds that we're completely ignoring, but it goes from the one to the other. So substitution, the bond order remains the same. And very importantly, when we're doing a substitution, the bond order remains the same, and usually, at least in the reactions that you work with, you must go from an alkane, something that's, not technically an alkane, but it must go from a single bond to a single bond. I'm going to take off the alkane. So when we do a substitution, it's very important that we usually have single bonds on both of the molecules, because if you had a double bond, you'd rather add in than swap one thing out for another. I draw a bit of a weird analogy there. I imagine this like a hotel, and if you've got a double bond, you've got open rooms, and if you've got a single bond, you're fully booked. Now, the only time that a hotel would ever kick out one paying guest to put in another paying guest is if they're full. If you've got an empty room in the form of a double bond, you would rather put a new guest, a side group or an atom, into the double bond, which is an empty room, than effectively chuck out one group to bring in another group. So whenever we deal with the substitution, the bond order remains the same, and it usually goes from single bond to single bond. The last type of reaction that we have is an elimination. In an elimination, you start with single bonds and you end with double bonds. So the important thing is that the bond order increases. Okay, the versions that we deal with at a matric level, in addition, you'll go from having a, double bond to having a single bond, always. And in elimination, you'll go from having a single bond to having a double bond. Now, obviously, there's quite a lot more than just that, but that is, for me, in essence, if I look at something and I can say, wow, I go from a double bond to a single bond, I immediately know that something that happened was addition. We get different types of addition, but I know that it was an addition. If I go from a single bond to a double bond, I know that something was eliminated. Something was taken out. Usually with elimination, we have to remove a hydrogen, and on this carbon, we either have a halogen, which we often represent with the letter X, or we have a hydroxyl group in the case of an alcohol. But usually the rule is, and please, this isn't really the terminology we use in matric, but you have a leaving group and you have a hydrogen. All right. On top of this, we get the kind of blurry edged groups. For example, combustion doesn't really fit into addition, substitution, or elimination, in my opinion. And the last one that doesn't really, in my opinion, fit so well with any of them either is polymerization. But many people will go and say, well, addition, polymerization fits under the addition reactions. And when we talk about the condensation, polymerization, they get a little bit funny about where that fits into. But we'll get to that point later. All right. So can I just quickly check at this point? Is everybody with me? Do you kind of understand the little bits that I've spoken about? Because what I'd like to bring in now is a bit where we look at each kind of reaction. We're going to build up your knowledge slowly but surely, focusing on general reactions, then substitution, then I'm actually working from notes here, then substitution, then addition, then elimination. All right. It's also very important with this section that you make sure that you understand the reaction conditions. It's not good enough to go, oh, it just happens. You need to know that you need to put in heat in certain cases, or you need to add, I don't know, an acid catalyst, whatever it is that you need to do, you need to be aware of what's happening. All right. So the first specific kind of reaction that I wanted to speak with you about is called a combustion. Now, a combustion reaction follows a general rule. Firstly, we have a fuel, which is usually a hydrocarbon. Okay, so it's usually an alkane, alkene, or alkyne. Usually they pick on alkanes, but it could be any of them. It will react with oxygen to produce carbon dioxide and water vapor. Now, I find that a combustion reaction sneaks up on you. It's one of those reactions where suddenly they're talking about methane reacting with oxygen, and you're stumped. In your exam, you're like, my gosh, when methane reacts with oxygen, does it make an alcohol? And you start thinking all kinds of crazy thoughts because you're not used to seeing a combustion done as a reaction. You're used to somebody saying to you, oh, look, it's a combustion. What happens? And then you can do it. But for me to hide it, not having told you this was part of combustion, and just to say the product that we have reacts with oxygen, many of you, when I say reacts with oxygen, don't equate it to burning. This combustion is literally burning. I can draw in here a little flame for you, okay? So it's literally something burning in the presence of something else. We have got a full-on fire going there. All right. The only trick that you really need to know with a combustion is, first of all, that it is always going to be exothermic. When you burn fuels, which your alkanes typically react as, they will give off heat. Some people like to put the heat in as a product. I generally avoid that because I like to restrict my my use of products and starting materials properly, but it is exothermic. Now, the way that you could write that is that delta H is negative. It gives off heat. Now, the only thing that we can expect you to do with combustion is we can test you on, write down the equation of a combustion. Is it endothermic or exothermic? What are the products? And then lastly, we can test you on incomplete combustion. We can also test you, which is what we're about to do now, on balancing equations. Write down the balanced equation for the combustion of methane. Or write down the balanced equation for the reaction of methane with oxygen. So I know I'm going back quite a way for some of you. I need to remind you how to balance an equation so that you don't lose marks. So I do this very slowly each time because I want to make sure that nobody loses any marks. You look at your number of carbons, hydrogens, and oxygens. Over here, we've got 1 carbon, 4 hydrogens, 2 oxygens. Over here, it's 1 carbon, 2 hydrogens, 3 oxygens. So my number of carbons is balanced, my hydrogens is out. So in order to get to the higher number there, I should put a 2 in front of water. 2 times the 2 there makes this become a 4. And 2 times by the oxygen makes that 2. Don't forget about those 2, which makes our total number of oxygens 4. And to have an equal number of oxygens on both sides, we must put a 2 in front of that, which makes this balanced. The only way that they can really test this is to ask you to burn things. Now, just a little note with regards to which things burn. Methane is commonly known as our natural gas, and it burns. Propane is what you buy when you buy gas for a gas heater or a gas stove. You're mainly buying propane. Butane is what we use in cigarette lighters. I'm just going to call it lighters generally, but cigarette lighters, sometimes even those lighters that they use for braais. Bic makes a really nice one that it's got a long end and you can use it to light a fire. Okay, so those are propane, are butane. Propane doesn't do so much. Hexane a little bit, but mainly after that it's octane in petrol. Okay, technically octane and hexane are present in petrol, but usually we've got 93 or 95% of octane, and the balance is hexane and other things. So our petrol is mainly octane. So these are the common ones that they could rather easily ask you to write down a combustion reaction. Now, many of you have probably learned about the idea of incomplete combustion. Maybe not necessarily this year, but you've definitely learned about the idea that there isn't always enough oxygen for things to burn completely. If we have incomplete combustion, it makes a really good multiple choice question. And the thing that you need to appreciate is that if you have incomplete combustion, our rule changes. It's fuel reacts with oxygen, and we produce carbon monoxide and water. Now, the reason it's so important to know this is that many of you, instead of just producing carbon monoxide, which by the way is very important because it's poisonous, some of you feel the need to, oh my gosh, we've got to get rid of oxygen somewhere, so you want to shortchange your poor water and turn it into hydrogen. That doesn't happen. So you need to make a note to yourself that complete combustion produces carbon dioxide. Incomplete combustion, where there is a shortage of oxygen, instead produces carbon monoxide, which is poisonous. There is a very good why you don't do it in a closed room, why you'd avoid it kind of explanation. We usually avoid as much as we can incomplete combustion. They used to have issues years ago with stoves in America, where if you did an incomplete reaction, you could produce carbon monoxide. A large number of people would try to kill themselves by sticking their heads in the stove and having carbon monoxide effectively poison them. After that, I think that was in kind of the 1960s to 80s. After that, they went and changed the mechanism so that you do not get incomplete combustion of gas in the stoves producing carbon monoxide, because there were so many people committing suicide that way. They removed it and people stopped committing suicide. Okay, so the number of suicides went down significantly. All right, can I just quickly double check at this point? So I'm going to quickly stop sharing for just a second. Who would like to quickly do an example on combustion, and who feels that they really get the idea and we can move on? So I'm going to start with who would like me to do an example on combustion. Perfect. I'm going to be really mean. We're going to do one on incomplete combustion just to check that you get the idea properly. Okay, so the question here was, ma'am, if it's incomplete, will they let you know? They have to, but they'd go and say, write down the equation for the incomplete combustion of something, and you'd have to figure out how it works. All right, so we are going to do exactly that. Please quickly take a screenshot if you need a screenshot of the combustion. Okay, so if we now do an incomplete combustion, I'm going to deal with the example, and this could potentially happen inside your house. Let's pretend. We have propane, which is our gas that we buy in those LPG bottles. And I'm going to tell you here the reactions. You're going to write down the reaction, the balanced chemical equation technically, for the reaction of propane and oxygen, but I'm going to tell you here that it is incomplete combustion. That means that for whatever reason, we have less oxygen than we'd ideally want. All right, I don't know if there was a question there. So the first thing that you'd need to be able to do is to get the formula, the molecular formula of propane. You should know by now how to count in chemistry. It's meth, eth, prop, but, pent, hex, hept, oct, non, dec, but you don't go further than 8, so you can stop at oct. Tasneema, I'm not certain if there's a question. Please, if there is one, just ask. Okay, you keep popping up. So my propane here has 3 carbons, and I know that it's an alkane, so it must have the formula CnH2n plus 2. So therefore, I assume that propane is C3H. 2 times 3 is 6 plus 2, C3H8. We adding in oxygen. Please remember, oxygen is always diatomic. You're never going to be adding in monatomic oxygen. It doesn't exist. Our products here, because it is incomplete combustion, are going to be carbon monoxide and water vapor. So your entire task right now that I'm going to ask all of you to quickly attempt is to balance this equation. Okay, so I'm going to pause right now, and I'm going to give you a quick chance to balance it. I know that for some of you, balancing is really easy, but you're also very out of practice. So please quickly do this. All right, I'm going to do the same. Okay, please, can I ask you to give me a thumbs up when you're done? Great. Perfect. All right, this one's one of those rather nasty ones where you get to the point where there's something that's diatomic and you want it to be a number and a half. And I'm going to tell you my little secret. It's okay if it's a number and a half. So when I balanced this, the first thing that I realized was that my number of carbons, I had 3 carbons here. So this had to become 3. So I put the 3 in front over there. The next thing that I did was my number of hydrogens here was 8. So I had to change this. So we also had 8. At that point, when I counted my number of oxygens up, I ended up with a rather nasty number of 7. Now, I have a little trick with balancing equations because otherwise they drive me insane. I want there to be 3.5 oxygens, and you know what? You're allowed to have 3.5 oxygens. That makes everything balanced. But your teacher's not going to like me if I let you leave it as 3.5 oxygens. So the rule is as soon as your balancing number becomes an and a half, everything must get times by 2. So this gets a 2. This was 3.5, so it becomes 7. This was 3, so it becomes 6. This was 4, so it becomes 8. And at that point, everything will also double over here. Not that there are any marks for showing working out. So it doesn't really matter if you leave that completely blank. But that is how I do these, is that I get very frustrated when they're half oxygens and I only want half of an oxygen and it's an even number, or it needs to be an even number and I want it to be an odd number. So then all that I do to make it work pretty quickly is I put in the half number, make sure it's perfectly balanced, and then double everything. All right. I hope that this makes sense to everybody. I'm not going to spend too much more time on this, but it is important that you understand the difference between complete and incomplete combustion, and that you know that you get water in both. This question more often than not pops up in multiple choice with them trying to catch you by saying, here are four possible balanced equations for the incomplete combustion of this fuel and oxygen. And then they catch you because one of them will have carbon dioxide and water as a product. The other will have carbon dioxide and hydrogen. The other will have carbon monoxide and water. And the last will have carbon monoxide and hydrogen. And you've got to tell them with a proper balance equation, obviously everything else is balanced, which of those could be your possible outcomes. This would be your answer if it is complete combustion. And that would be your answer if it is incomplete combustion. Something else that I am almost certain that you're not going to get, but just in case I'm going to mention it. I saw recently, not in our local questions, but in an international exam for Cambridge A-levels, that they told a student that you have a combustion reaction, but you make a solid, and you had to write out a balanced equation. I doubt this will ever come up. But what you had to do in that circumstance was instead of making carbon monoxide or carbon dioxide, you actually just had to make carbon. It was a very weird question, and you'd kind of carry on with the same thing where you learn your rules and it's fuel plus oxygen gives you carbon dioxide and water vapor. But in this case, you had to make sure that carbon was also one of your products. But I really almost certainly doubt that we will not see that. I think that it would cause way too many issues with way too many people getting confused. But I saw it for the first time just this last week, and it made me go, wait a second. When we burn things, we often do end up with charcoal left at the end. It doesn't all magically turn into gas. So it made me stop and reconsider just for a second that it's something where if they do ever throw it in, you want to be prepared to say, actually, when things burn, we can have some just carbon left over as a solid. All right, but don't put that in as a routine thing. That is like your 1 in a gazillion if they say it first. All right, please can I ask you to take a screenshot of anything that you need because I'm going to clear. We are now going to move on to substitution reactions. So we're going to be talking substitute. I've just got to check that I've got my spelling right. There we go. To substitution. There we go. Substitution reactions. Some days my brain leaves me. All right. Now with the substitution reaction, it's a little bit like a sports game. If you've got 15 rugby players on a field and you take one off because he's injured, you can put one in as a replacement. You can't take off you can't put in one without taking one player off. I know some of you are going to be correcting me on that. Let's just quickly go back. Sorry, is combustion classified as an addition reaction? I don't like classifying combustion as anything other than an oxidation. But so it isn't technically substitution. That's why I deal with combustion first. Combustion is an oxidation reaction. We don't teach you other oxidation reactions. So it's easy for you to just think of it as a reaction that falls into its own category. All right. Now when we're dealing with substitution, we swap one thing for another. So I'm going to start with the first type of reaction that we can have. If we have an alkane and we react it with a halogen, in the presence of UV light and heat, we heat. We can produce a haloalkane and usually an acid. Okay, so this is a general overview of the first type of reaction that you can get, and we're going to call this type of reaction a halogenation. We can be more specific about the kind of halogenation depending on what halogen we add. If our halogen that we add is Cl2, then we can call this chlorination. If the halogen that we add is F2, then it's fluorination. If the halogen that we add is iodine, it's iodination. You get the idea. Okay, so you may refer to the type of halogen specifically, or halogenation specifically, by the halogen that you add. So I'm going to quickly discuss with you a couple of things around this reaction. So if I start off with a halogen, sorry, with an alkane, if I start off with an alkane and a halogen, the alkane only ever has single bonds. And in this case, the halogen must be diatomic. So for example, if I do Cl2, I need to provide ultraviolet light. Now, you do not need to know that ultraviolet light effectively breaks the chlorine bonds apart and gives one electron back there, one electron back there, and makes something called a free radical. You don't need to know that. You can just smile. What then happens is that free radical goes and bonds with a hydrogen. When it bonds with a hydrogen, this becomes HCl, which in this case I'm regarding as my acid. What's then happened is that this H has left the building. All of these guys have all run off together, which leaves a situation where for a very brief instant in time, we have a radical sitting over there. We also, if you remember, had one chlorine radical that was left over. The one went and stole the hydrogen and became HCl. The other still left behind. And these two will react with each other. And when they react with each other, this chlorine will go and join in that position. Now, I've just shown you the real-time motion of everything that happens. You don't need to worry about all of that working out. What you need to know is, oh my gosh, when I start off with this and I put in chlorine, one and only one of the hydrogens will be taken away and replaced with the halogen. And therefore, I end up with HCl as my product. Okay, so this specifically is called a halogenation reaction. Sorry, I'm just going to quickly remember to get rid of this. Okay. All right. Tasneem, do you have a question?
Yes,
Yes,
ma'am.
Tasneem. Yes, what's your question?
So we don't use Mckovniecovs rule in this instance.
No. Mckovniecovs rule is for, I've just got to get this. Is for your addition reaction, Mckovnikov addition. This isn't an addition, this is a substitution. I have fought long and hard with other teachers about which position the chlorine goes to. And in theory, if you use the same principle as Mckovnikov, this is the more substituted carbon. So in reality, you'd expect the chlorine to go to position number 1. In reality, what we find is that position 2. We find that position 1 often is just the case. So my advice here is there is no preferential placement of the chlorine. We've come up with a rule that says you always put it in position 1. It's easiest, okay? But if this product then later on goes and reacts with something and magically the OH goes to position 2, that tells me that in this original version, they intended for the Cl to go to that position. So there is no actual rule as to whether the chlorine goes on carbon 1 or 2 or where it goes. But if you later look at a subsequent reaction, which told you that your leaving group had to be in the second position, then you'd make it in that position deliberately. But there is no rule that says that it specifically has to go on any one of the carbons. I know I actually fought it from a mechanistic point of view, which is dealing with the radicals. The radical would be most stable on the center carbon. But when I looked up in literature, most of these reactions actually end up producing 1-chloro-propane, which didn't really fuel my argument very well. Okay, now we can do this. This specific halogenation, by the way, is our chlorination, because we are adding in a single chlorine. Please, this is not hydrochlorination. We haven't added in an H and a Cl, we've just added in a Cl. So I'm going to ask everybody here, and I'm going to just suggest that you put your halogen on carbon 1. Please, this is carbon 1, but if you put it on this carbon here, this would then become carbon 1. So it doesn't really matter which side it's on as long as it's on one of the ends. And if you put it on the middle, we'll go with that as well today. Okay, so there isn't any real preferential placement that you learn for substitution reactions when every one of the hydrogens is equally possible. You'll see just now if we do a substitution and there's already a good leaving group, like if I were to substitute this haloalkane, it will be substituted on carbon position, this chlorine, that's the position another group would go to, because it's a little bit like swapping a goalkeeper with a goalkeeper. But here, nobody has positions. All of the hydrogens are equal, so it can technically go anywhere without there being an issue. So I'm going to ask everybody, and I know I'm being very vague here, but I want to check how much you can do, to tell me the reaction, or write down the equation of the reaction for butane in the presence of bromine and a UV light. Without this ultraviolet light, this reaction will not happen. So it specifically requires ultraviolet light. Please note that there is enough UV light in sunlight for many of these reactions to happen. So you'll sometimes see that if we don't want these reactions to happen, we make the reactions happen in the dark. So if we exclusively want to do another reaction and not risk this reaction happening, we remove the UV light and it usually works. So can I ask everybody right now to please write down another halogenation reaction, but this time you're doing a bromination for me because you're adding bromine. I'm going to pause for just a second and give you a chance to do it. All right, go for it. This is also checking just a little bit that you can draw all of the molecules that you need to be able to draw in order to be able to figure out how everything fits together. Okay, so I've just had a very good question from Sarah, which you'll see that I've done in my answer now. If I tell you specifically to use structural formulae, I actually made a mistake in my first answer. I haven't in my subsequent one. You can see I'm not writing anything further. I'll show you what I did just now. But my chlorine should not have been written as Cl2. It should have been written as chlorine Cl-Cl, because when we're doing structural formula, we should show every single one of the bonds. So I have done that in my subsequent working out. When I did the first one, I was kind of doing a general overview, so I didn't expand it out. So Sarah, you're 100% right. I should have done the chlorine showing the bond in between if I told you specifically to do structural. Okay, can I quickly ask who's already done with this? Give me an indication, thumbs up when you're done so that I can know when we can move on. Okay, well done. Okay. All right. In the interest of us making it through all of the sections today, I'm going to push you just a little bit for time because I've still got to go through 2 more substitution reactions before we look at anything else. But I really would rather that you understood it, even if it means that we drag this section over and we don't do practice until Thursday. Maybe this counts as your practice, but for some reason I find that in an exam, the reason it's tricky is it isn't like them going, you're going to do a halogenation. They'll go, here's the stuff, do it. And you've got to go and figure out that it's a halogenation first, which is probably the hardest bit. All right, so sharing my screen. There is my butane. There is my bromine with its bond. I didn't put in the UV again, but it's technically UV, and you should indicate heat. Just so you know, there's a shorthand. Triangle in chemistry shows heat. Okay? Over here, your bromine could have gone on any one of the hydrogens, as long as only one of them got replaced. Then you had to be very careful here. You had to show HBr, but I was a little bit naughty. I did the one, not the other one. If I wanted to not lose a mark here, this should technically have also been a BR. Okay, so I should have had H-BR. So I'm going to quickly go back in here and remind you that if you are asked to do structural formulae, technically everything should be written out with its bonds. Otherwise, they get really fussy and you lose your marks. All right, so this is the only reaction that specifically needs UV light. Will you lose marks if you forget the UV and the heat? You won't lose it for the writing out the equation. Usually for reaction conditions, they have to ask for them separately. So they will then ask you to write out the balanced equation using structural formulae, and then in a later question, they'll say write down one reaction condition. It's very rare that they say write down all of them, but sometimes they sneak around it by saying, other than providing heat, write down one other reaction condition. The one that you need to remember here is UV light. UV light, without it, this reaction will not happen. If I put butane and bromine together in the dark, nothing will happen. Without UV, we don't create the free radicals. The free radicals don't initiate the reaction, and we therefore don't end up with a product. All right. I presume that everybody here is okay with the idea of halogenation, that it's called halogenation because you add in a halogen. Also, you only add in one halogen, okay? Very important. One halogen per molecule, not two. Okay, it is possible in real chemistry to add more than one, but then you've got to change some of the reaction conditions, and we don't cover that in matric. In our examples, you add in one at a time, and that's all that you care about. All right, the second type of still substitution reaction that I'm going to look at is called hydrolysis. Now, hydrolysis always causes huge issues because you've all learned about hydrolysis from the perspective of acids and bases. And it's still kind of the same here, but it isn't. So technically the hydrolysis reaction here is still a reaction of something with water, but it gets a little bit more complicated. So in our hydrolysis reaction, we must always start with a haloalkane. My words are coming out faster. With a haloalkane. So we start with a haloalkane, and we have a choice here. We can either add dilute strong base, or in a completely separate reaction, just water. So either of these two will work. And the product that we get is an alcohol, and in the one case where we did a dilute strong base, we get a salt. And so the salt was the one option. Or if we used water, we instead get an acid. Now, when I talk about an acid, I mentioned acid last time. That was because we produced HCl or HBr or HI or HF. All of those are what I mean by acids. When we instead produce a salt, that is because our strong base would either be KOH or LiOH or NaOH, and therefore we would either produce KCl or KBr or K whatever it is. We could produce LiBr, we could produce NaF. So the idea is what salt you produce or what acid you produce depends on which halogen you had in your haloalkane. Also, if you used water to begin with, you will end up with an acid because that's where the hydrogen comes from. Okay, so this is a rather complicated way to explain it, but those are pretty much your options. So this could be the haloalkane that we made in our previous reaction. So in our previous reaction, one of them at least, I think I produced, what would this be? 1-chlorobutane. Okay, so if I've got 1-chlorobutane, now it is in position number 1, and I react it with lithium hydroxide because I feel like it. What's going to happen is that the hydroxyl group, technically the hydroxide, it's still a hydroxide while it's OH minus, the hydroxide is going to swap out with the bromine, the halogen. Okay, and if we're being 100% correct, yes, I do have to go and show in all of the individual bonds, but we'll get there later. We're not showing mechanisms here. So what's going to happen is those two are going to swap, and they swap exact positions. So here, the OH has to go where the Br was. That means that if the bromine had been on position 2, then the hydroxyl group needs to go to position 2. All right. So that over there is the alcohol that I produce. And then we're going to discuss just a little bit further here. I'm going to take away these options because I have to commit to what we really get. In fact, maybe we'll just regard, we're going to regard everything that's above this line here as being something else. Okay, so this is not part of what I'm doing right now. The other product that we're going to get is made up from the bromine and the lithium. So specifically here, we're going to have LiBr. And if we want to show, I mean, I'm not going to really, I don't know if I really want to put in a bond here because technically this is Li plus and Br minus, and they're not bonded together. They are two ions that are hanging out. Okay. All right. So I hope that this makes sense. With our hydrolysis, we always have to start with a haloalkane. We always have to produce an alcohol, and we will also produce something else that goes with it that's produced when the two groups kind of split apart. All right. So can I quickly ask right now, I'd like to give you one to do. I'm going to do it in a different color so that I don't have to divide up my screen again. But what about if we started with this, so 2-chloropropane, and I reacted my 2-chloropropane with water. Okay, I'm going to draw this out as structural formula here. So there's water. I would like everybody to please look at this and tell me what two products they think we're going to get. All right, I'm pausing while I quickly do mine, and you can do the same. All right, please indicate to me when you're done. Are there any reaction conditions? The reaction conditions usually are that we just need heat and reflux. All right, so when we're talking about heat and reflux, it means we usually stick it in a round bottom flask. We heat it on top of water. We usually don't heat things on an open flame because with organic chemistry, so many things are volatile and flammable. So we just heat this kind of in a water bath. The water bath is almost like, I guess, a giant kettle where the kettle's maybe boiling or heating it up, the thermostat's heating it up to a certain temperature, and then you just stick the reaction in there and the reaction happens on its own. All right, ladies and gentlemen, I think I did most of this for or with you. So I'm hoping that most of you have got the answer. So my answer over here is that I'm going to do a substitution reaction, specifically a hydrolysis. They often ask you the name of this reaction. It's one of those like fun questions to ask. And what you'll see is happening here is that the chlorine gets replaced with the hydroxyl group. Okay, so those two swap. So there's a hydroxyl that goes there. And then the hydrogen, technically, that's left over here, I'll do it in a different color. The hydrogen that's left over here joins with the chlorine and we make HCl. Okay, so in this case, because we used water here, we have to use HCl there. All right, so our reaction conditions in this case are simply heat and reflux. Reflux means that you effectively put the whole reaction in a volatile solvent, and as the solvent boils and condenses, it mixes everything up for you. All right. Does the OH group have to go on the second carbon? This one is non-negotiable. Because you'll see I did it even over here, because this is in position 1, this is in position 1 as well. This is in position 2, this is in position 2 as well. There are certain chemical reactions that you will learn at university level if you do them, where we can get things to move from one position to another. But at a matric level, we assume that we're swapping one position with the same position, and at least our reagents that we're using are the ones that will only swap from one position to that same position. All right, so effectively the chlorine being present here is what's going to make this carbon a good place for this OH minus to join in. Okay, not going into the details, you don't need to know them particularly. All right, I hope that that makes good sense. I'm now going to move on to the next type of reaction. I don't know if we need to do multiple practices on these kind of things, but I think as long as you get the idea that you could use anything. For example, if I'd used KOH here, I hope you all appreciate that I'd then have got KBr. So how things change, you've got to make sure that all of your bromines go from starting materials to products. If you had a group 1 metal ion, that it ended up in your products, etc. Okay, so far we've looked at an alkane turning into a haloalkane. That was our halogenation. We then did a haloalkane turning into an alcohol. That is our hydrolysis. And the last type of reaction that we're going to be doing right now is the reaction of a hydrogen halide with an alcohol. So technically, we always call this the reaction of a hydrogen halide with an alcohol, but there's a catch. This is also potentially known as halogenation. So there are two kinds of halogenations. Now in this kind of halogenation, I start off with an alcohol. I react it with a hydrogen halide. You need to know what all of these terms mean. I then produce a haloalkane and water. So this reaction is almost the exact opposite of what we did before. In the previous reaction, you took a haloalkane, you reacted it with water, and you got an alcohol and a hydrogen halide, which I previously called an acid, but technically it's a hydrogen halide if we're being more specific. All right, just give me 1 second. I need to check the questions. So this is still a substitution, and both of them can potentially be called hydrogenation. It's just which different kind of hydrogenation we have. So in the one, it's hydrogenation from a, it's halogenation. I haven't yet done. So wait, let me go back and check what the question was. I think I'm using big words that are wrong. Give me just 1 second. Which one would be hydrogenation? I haven't done hydrogenation at all. Okay. There wasn't a hydrogenation at all. We only do hydrogenation when we do an addition. So this would still be a halogenation. Okay. Yeah, we're still on substitution. Sorry, I've just got to try and get into the right place. I can't open the chat. Okay, could you call this reverse hyd? I wouldn't. I would not call this a reverse hydrolysis anywhere other than maybe in my head. Okay, so if we start with an alcohol, I'm going to go with a very simple alcohol. I'm going to go with methanol. And I reacted with a hydrogen halide. That is something like your HCl. Okay, now there's a difference between what I was calling an acid. Before, everything I was assuming was dissolved in solution, so it technically became acidic. But if we're viewing this as being a gas, then it's hydrogen chloride. If we're viewing this as being in solution, then you can call it hydrochloric acid. This will go to produce a haloalkane. So the OH hydroxyl of the alcohol will get replaced with whatever halogen, well, halide technically, you've got in your hydrogen halide. So those are going to swap. And we end up producing that, which is chloromethane. You technically could call it 1-chloromethane, but the 1 is unnecessary. There's only one place for it to go. And what's left over? Well, we have our OH left over and our H left over. So that is what makes our water. All right. So as a rule, it's always an alcohol. It's always a hydrogen halide. Okay. From there, we're going to produce a haloalkane and we're going to produce water. I would like to quickly give you one of these to do. And I'm going to, in the process, also be testing that you know how everything fits together. So I'm going to ask you to please draw 2 butanol. Some of you may have referred to it as but and 2-ol. It's the same thing. And I would like you to please react that with hydrogen bromide. I'd like you to write out the full reaction and show me what products you get. All right, please, I'm going to pause quickly and I'm going to give you a chance to do that. Reaction conditions here were non-specific at all. I'd say that the only reaction, if someone really pushed me, because there aren't any that I've got down, is you might say that you'd still put in heat. And the other thing that you might say is because you're making water as a product, you'd try to make this possibly, it wouldn't necessarily be ethanolic. I don't think there are any very specific reaction conditions with this. I don't have any that I've got down in my notes as being like crucial. All right, so reaction conditions, if you're desperate, are adding heat. And I'm going to say technically you don't want too much water to be put in here, but I'm not going to say that you should do it to the point where you say remove water, because water is one of your products. It's just that if you do have water in here, you could technically favor the hydrolysis reaction to happen again, which means you're making your product and then immediately using it up. So you technically would ideally do this in an ethanolic solvent if you want it to work well. All right, I'm going to quickly do this. You will do the same. I'll get to the question in a second. This reaction doesn't use a catalyst. Nope. So far, we haven't covered a single reaction that uses a catalyst. Most of your addition reactions are the ones that are weird and use catalysts. Okay, please can I ask you to give me a thumbs up if you're done with that? Okay, fantastic. All right, we're going to jump straight back in. So if you look over here, I've got butanol. This is 2-butanol because it's on carbon number 2. Here's our hydrogen bromide. Effectively, what's going to happen is the hydroxyl group will get replaced by the halogen, and we'll end up with the bromine in that position and water. Now, it's very important that you start, as you're doing these, actually trying to name them, because that's a very good skill, because quite often they're going to ask you to draw them. They also might ask you to name them. So this here would be 2-bromobutane. All right. So the reason I'm suggesting that you start naming them is we haven't yet started having to consider major and minor products or anything like that. But we're going to be doing that in the next section, and I need to make sure that everybody is good with that. All right. So ladies and gentlemen, at this point, I've gone through combustion reactions with you, and then through substitution reactions, where an atom or a group of atoms is replaced by another atom or another group of atoms. And very importantly, your bond order remains the same. So you go from single bonds to single bonds. We've specifically looked at halogenation, hydrolysis, and the reaction of a hydrogen halide with an alcohol, which is also known as halogenation. So here we could refer to this reaction as being bromination. No, that isn't, because that involves chlorine. So let's go with chlorination. There we go. And this would be bromination, because we have Br being added in. All right, quick question. Is it a problem to write water before the haloalkane? Absolutely not. The rule always here with your reactants and products is as long as both of them appear and they're both on the right side of the arrow, and ideally you've got pluses between them as well, which I've been avoiding a bit. As long as you've got everything on the correct side, it doesn't matter which order they're in. So if you particularly want to write them down out of order, that's not an issue either. All right, so those were all of the substitution reactions that we've looked at. We're now going to quickly move on to our addition reactions. Now, to remind you, in an addition reaction, you are always going to have a double bond going to a single bond. But there are certain rules with regards to where things go if there are, I'm going to use the word asymmetrical, it's not technically the word, but if the thing that we're adding across the double bond doesn't have the same kind of atom on both sides. There are 4 different types of addition reactions we're going to do. Please note that only 2 of them are going to involve Mckovnikov. So with addition reactions, Mckovnikov, just checking on my spelling, Mccovenikov is a rule that you need to consider, but you're not going to consider with the first 2 types. So the first type of addition reaction I'm looking at is called halogenation. Now I know you're going, wait a second, we did halogenation before. Halogenation involves bringing in a halogen. We can do this a number of different ways. So we're always going to start with an alkene. We're always going to add in a halogen. And when I say a halogen, I mean diatomic. So Cl2, Br2, I2. Okay? We're going to have different examples later where we do hydrohalogenation, and that's adding in a hydrogen and a halogen. We're then going to produce a haloalkane. And the last, that's all. We only produce one product here. We don't have another product. So that's one of the ways that you can sometimes tell addition reactions, is you usually, everything fits nicely into the double bond, and you don't usually end up with leftover products. So if I started very simply with an alkene, I'm starting with ethene, and I reacted it with chlorine gas in this case. The only important reaction here is that there must be no water present. If I have water that is present, the water then competes, and we may technically put in a hydroxyl group on one and a hydrogen on the other, and we end up making an alcohol. So your water is also a reactant, so we can't have water present here. What's going to happen is this chlorine, which if you're asked to draw a structural formula, you should put it out separately. One chlorine will attach on either end of the double bond. Sorry, we'll no longer have the double bond, and we'll have a chlorine there, a chlorine there. So your chlorines or your halogen ion atoms are always going to go what we call in a 1-2 position. This position, next to each other. And that is your product. So if we practiced our naming over here, this would be 1,2 dichloro ethane. All right, I hope that that makes sense. Please note, because both chlorine atoms are identical, it doesn't matter which one goes where, it will still look the same. Next thing is positions. A lot of this we get a lot more, or you guys get a lot more fussy than you need to be. If you've got a Cl there and a Cl there, it's still correct. If you've got both on them on the bottom, it's still correct. The only time that it isn't correct is if you've got both of them on the same atom. That is a no-no. This one I'm crossing out so you can see it's a no-no. All right, so you have to have one chlorine atom here going to each side of the double bond. If you remember in our first lesson, I went on and on about every carbon having 4 bonds. In this case, it still applies, but each of the groups that get, well, each of the atoms or groups that get added in, one must go to each of the positions. All right, can I ask you just quickly to draw for me the reaction between propene and bromine gas? The reaction condition is that it is done in ethanol. That means no water, and I'd like to see the products. Can I ask you please to do this? I'm going to pause so that we can quickly get going. All right, go for it. You've got to draw out the full structure.
Ma'am?
Yeah?
Sorry, it's not letting me type for some reason. But I wanted to ask, right before you started addition reactions, you said like the basic, like 2 or 3 like basic rules for all addition reactions.
All addition reactions, you go from a double bond to a single bond.
Okay, thank you.
That's my rule. You can also view it as you are adding things in across the double bond. That also, I guess, is an explanation of it. Okay. Is it just this specific one that's done in ethanol? A large number of your addition reactions have to be done in ethanol, unless, of course, you're actually aiming to add in water. So, for example, the hydration reaction, you want to add in water, then you put in water. But if we're doing hydrogenation, we generally, we don't actually specify it, but a hydrohalogenation is also no water. So water just does a competing reaction, so you don't always want it to be present because it can, from this reaction, produce an alcohol, and you don't want that alcohol. Okay, I hope I've answered everybody's questions as they're coming in. Please also try and name your product just to get into good habits. Okay, please give me a thumbs up if you're done. Okay, fantastic. All right. So over there, that's what I've done. There's my propene, there's my double bond. Please, it doesn't matter if you did the double bond here or here. Propene, as long as you got a double bond, it's going to be, this is going to be carbon number 1. 1, 2, 3, because of where I put the double bond. There's my bromine gas. And when I add it in, 1 bromine is going to go to carbon 1, 1's going to go to carbon 2. So there they are. Once again, it doesn't matter if they're above or below, as long as 1 is on carbon 1 and 1 is on carbon 2. And the name is 1,2 dibromopropane. All right, so this over here is a halogenation reaction. Because we added in chlorine, the top one is specifically called a chlorination, and the bottom one is specifically called a bromination. Okay, so sometimes in an exam, they ask you to write down what kind of reaction is it, and you actually have 3 options because it's an addition reaction, a halogenation, and a chlorination. Sometimes they get smart and they say, what kind of addition reaction is it? And then you can't say addition reaction. So you can say halogenation or chlorination. Both are equally accepted. I usually put in both. If they ask you what type of halogenation is it, that's when you commit to chlorination or bromination. Sometimes I find when I get asked what type of reaction is it, I write all 3. It's probably horribly unnecessary because I know only one of them is needed for the mark, but it's just worth noting that you can do those. Please note we're still on addition reactions. I'm just doing the next type of addition reaction. So the next type of addition reaction that we're going to be looking at is hydrogenation. Now, hydrogenation and hydration get people very confused. Hydrogenation is adding in hydrogen, which is also known as hydrogen. Okay, so hydrogenation is adding in hydrogen. This reaction is used to make margarine. Okay, so if I start over here with my propane and I react it with hydrogen gas, in the presence of a catalyst. We finally reached a catalyst that you need to know. And the catalysts here that you can use are platinum, palladium, or nickel. any of those. I recommend you cheat and you learn only one, maybe two. Those are the two they more commonly pick on. But you learn just one, because if they put it in, you go, yay, I'll go with that. If they don't put it in and you've got to put it in, as long as you know one of the three catalysts, you'll be fine. And then what happens here is across the double bond, hydrogen will add across it, and we will produce our alkane. This is one of those very special reactions because we turn an alkene into an alkane. All right. This reaction, as I mentioned, is used in the production of margarine. It's also one of the reasons why people often will go on about margarine having so many atoms different from plastic. Believe it or not, plastic is also a very long chain alkane, mainly in its structure. So what we do effectively if we make margarine is we take an oil. Our oils are unsaturated fats, which means that they got those double bonds. We bubble in our hydrogen, we bubble it through with a catalyst, and we end up producing our fat. The difference between an oil and a fat is that a fat usually is saturated. Because it is saturated, it's only got single bonds. There's also a justified reason as to why one is runny and liquid and one is solid. When you end up producing alkanes that are alkanes which are saturated, they become very nice regular shapes, and you can pack them nice and close together and make a solid. If you instead have things that are unsaturated, these double bonds mess up the structure and makes them, the scientific term is literally kinky. They've got kinks in them and they go all over the place. And because they're so unruly, you can't pack them close enough to make them into a solid. So therefore they remain far apart, can move over each other and form an oil. All right. So you need to know about your hydrogenation. Usually it's not the most examined question, but it can come up, so it is important that you know it. All right, I'm going to quickly do one here just that you can all have an opportunity. So we're going to start here with ethene, and when you react this with hydrogen in the presence of a platinum catalyst, I would like to please know what product you get. Go for it. Okay, please give me a thumbs up when you're done. Perfect. All right. So over here, you can see what we get. We start with ethene. We add in hydrogen in the presence of platinum, and we get out ethane. We start with ethene and we get out ethane. All right. Don't worry, Bella. I completely understand. I'm very glad I didn't have load shedding today, so it isn't an issue at all. There will be a live recording, as always. I am still recording. Good. There will be a live recording. So if anybody does have load shedding at any stage, it's one of those things we unfortunately can't account for. My advice when there's load shedding is to do what I do. I plan ahead of time. I turn on my electric blankets so that my bed's nice and warm. And for the only time I give myself free each week, I just snuggle into my bed. So load shedding for me is very frustrating, but I've learned to just use it to let go. Please don't panic if you've got load shedding. All right. Okay, so I completely understand. In fact, I did notice we had a sudden drop in student numbers, and I looked at the time and I was like, ah, that explains it. All right, okay, so does everybody understand that this is hydrogenation? Please be very careful. The most confused section here is that people say hydration instead of hydrogenation. And it is one of those things you got to be very careful of because there is a hydration reaction. All right, I'm going to quickly move on because we've got about 20 minutes left. I would very much like to get very near to the end, if not completely done today. So we're still on addition. I'm going to write it in because I think it confuses you if I don't. So we're still on addition, but we're now going to be dealing with hydrohalogenation. These words are rather descriptive. Hydrohalogenation means that we are adding in a hydrogen and a halogen. That halogen could be chlorine or bromine or iodine. It's not usually fluorine. Fluorine's rather reactive. So as much as we hypothetically put it on paper, we don't do it that often. So when we're adding in hydrogen and a halogen, this could be hydrobromination, hydrochlorination, hydroiodination. Once again, different subcategories under the hydrohalogenation addition. So the important thing here is that I need to start with an alkene. I need to add in a hydrogen halide. I described them as acids earlier, same. And what you'll end up producing is a haloalkane. All right, so over here, if I start off with, now we got to be careful. If we start off with an alkene, because this, the reason I said we've got to be careful is this is where our Mckovnikov comes in. If we start off with an alkene and we add in a hydrogen halide like HBr, unlike the other two examples where they both had Br or they both had H, we've now got two different groups and we've got to decide, so does the bromine go here or does the bromine go here? And therefore, where does the hydrogen go? So I'm going to quickly just discuss with you what Mckovnikovs rule states. I do it a different way from everybody else, and I've recently found that my students really don't like my way, so I'm giving you both. I usually say that the more important group, which will usually be your halogen or your hydroxyl group, those are the only two things we're really going to do it with. So your more important group goes to the more substituted carbon. That makes perfect sense to me because I studied chemistry, and for me, the more substituted carbon's an easy thing to find. My students like the version which instead says that the hydrogen goes to the side that has more hydrogen. I think it's easier to apply. So it's one of those continuous cases of the rich get richer and the poor get poorer. So since there are already two hydrogens here, that is where the hydrogen will go to, and therefore the bromine will go to the other side. I'm going to quickly remove all of those scribbles because otherwise you're going to get very confused about what I was talking about there. And we're going to go and put it in as our reaction. So those two react. We produce something that's got 3 carbons as it did. We have everything here that I'm drawing here was here in the original. Okay, so I'm going to do this color coordinated. And then over here, I'm going to say that this is my H and this is my Br. The hydrogen is going to go to the side that's already got more hydrogens, and the bromine is going to go to technically the more substituted carbon. This carbon has only got 1 neighbor. This carbon has got 2 neighbors. This is more substituted. So my rule still isn't wrong, but a lot of people really like the idea. I think they find it really easy because you're always going to have a hydrogen to put somewhere. Putting the hydrogens where there are already too many hydrogens makes good sense. Your only reaction condition here is that there's no water present. And because there's no water present, that means we usually do it in ethanol. All right, so ethanol is our solvent. Okay, to check that everybody can do this particular type of reaction, I'm going to quickly give you an example. I would like...
Ma'am?
Yes? Yes, Bella?
Sorry, just before you carry on, I'm just a bit confused about something. When you use hydrochloric acid with prop-1ene, you come out with basically the same answer, obviously just with hydrochloric acid.
Yes.
But then you, in the book that I have the answer series, that one.
Yeah.
They added another. They added 1 more of the product.
2 of them. Oh, okay. So I'm cheating here. You remember I
Okay.
told you Mckovniecovs Rule says that we only would have this. The Mckovniecovs Rule says we're going to get 2 products. You're 100% right. This is what we call our major product. I often cheat and I don't want to put in the minor product. I'm going to be good and put in the minor product. So this is my major product. We will also get another product that is less favored, and that will be this product. But we usually do not focus on the product that is produced in a smaller quantity, which is why I skipped ahead a little bit. I'm used to usually putting in just the major product. So the major product is produced in a larger quantity than the minor product. Okay, so Mckovniecovs rule says which of the 2 products are going to be favored. Now, this is where the word favored becomes very important. Major just has more of it being produced than minor. There is no absolute rule. You can, if you're really lucky, end up with 95% major product and 5% minor. But realistically, these values, I think, are more in the region more often of kind of 70 and 30. Okay, so you will potentially have both products written down, but it's very important that you understand that one is a major and one is a minor. And each one of these will either become this or it will become that. Does that make sense? So if you put a 2 in front of here, some of them will react with the HBr and form the major product, which is 2-bromo-propane. And some of them will form the minor product, which is 1-bromopropane. Okay, the reason that I prefer not to put both in at the same time is it gets incredibly confusing for students to appreciate that it isn't actually a rule where there are 2 of them and one will be this and one will be this. I could put in 2 of them and they'll both form the major product. So it's just the idea that you appreciate that sometimes when we do a reaction, we end up with 2 slightly different products. And when I say slightly different, these 2 would have different melting points, boiling points. They could physically look different. They're likely to, you could separate them because they're melting points and boiling points. And that's one of the reasons why we know the ratio of the 2 products. You're never expected to learn it. In fact, I can't even offhand tell you what it is, but you need to know that the major product is the one favored by Mckovniecovs rule, which is why most of your examples won't focus on there being 2 different isomers that are produced. Okay, it will just focus on the major product. All right, did I answer your question?
Yes, thank you.
Okay.
I was just a bit confused because
Brilliant.
in one of my papers, I wrote both products and she was telling me you don't need to. I was just confused.
Well, that's why I'm saying is usually we focus on just the major product because it's what we're aiming to get out usually. We actually have a big problem if we're aiming for the minor product as our like goal product, because then we're going to have more than half of what we make not being what we want, which isn't ideal for anything where you're doing industry. So we usually don't write, so just very importantly, we can't have one thing reacting and producing both products. So what the exam question will usually ask is it will usually ask you, here's the reaction, write down the reaction to produce the major product or the minor product. And obviously they're going to focus much more on the major product than on the minor product. All right. It isn't a case that the minor product doesn't exist. I once saw a really weird exam question where it literally had block for this, and then 2 blocks here. And it caused so much confusion because everyone was trying to come up with 2 separate products without realizing there was actually 2 versions of the same product. So just be aware of the fact that this can cause endless confusion in tests if teachers or examiners choose specifically to deal with both the major and the minor at the same time. All right, let's move on to us doing a practice example here. So I want you to do, now my brain's just died. I want you to do 2-butene. And I'd like you to please react that with HCl. Please just be careful with this. This is something else that's been picked up that students often do wrong or incorrectly. There's a lot of people, instead of referring to this as a hydrohalogenation, are so excited to see the halogen that they call it a halogenation. You cannot forget that there was a hydrogen that also got added in over here, and over here. So you can't just call it a halogenation. If this reaction was an addition reaction, it must be a hydrohalogenation if you've only got one halogen atom. If you've got two, then that's fine. By all means, call it a halogenation because you didn't add in hydrogen, a hydrogen atom. Here you did. All right, so I'm going to quickly pause while you all have an opportunity to write down the answers. You will notice, if you're smart, that in this reaction we don't have a minor and a major product. Because of the symmetry, it doesn't matter whether it's a minor or a major. They're both the same and you only have one product. I'd like you to please name that product. Okay, please give me a thumbs up when you're done. Okay, fantastic. Bella, think a little bit longer about your answer. You've missed something. Okay. All right. Ladies and gentlemen, I'm going to quickly, thank you. You're going to see where you went wrong if you did. Most of you, I think, have already picked up your mistake. So we started off with 2-butene. We added in HCl. And here there wasn't a side that had more hydrogen. So it didn't matter which way around you went. Whichever way around you went, the chlorine would have been on carbon number 2 because of how you number it. So this would be 2-bromobutane. All right. I hope that that makes good sense to everybody. All right. So this is going to be 2-chlorobutane because we did our reaction. Yes, Tasneem.
Ma'am, the reaction on the right is 2-chlorobutane, not 2-bromobutane.
Oh, my goodness. Yes, my brain is not thinking. Thank you. There is a chloro instead of a bromo. Oh, I swear by the time I get to these lessons at the end of the day, my brain has packed up. Good thing is at least I know what's right and wrong when I recognize it. All right. And realistically here, just to quickly point out something to you, your butane, there should be no gap between the chloro and the butane. I sometimes like to leave a little space, but it should be so small that you can justify that it isn't a space if anyone queries it. Okay. You want the examiner to be able, if they're getting fussy, to go and say there isn't a space. Okay. So yes, you're 100% correct. That is the case. So over here, this top reaction would be described as an addition reaction, a hydrohalogenation, and then specifically a hydrobromination. Bottom reaction, and I'm now making up for my last mistake, is going to be a hydrochlorination because we specifically added chlorine. All right. I think what we're going to do this evening, just to make sure that we end at a nice point, is I'm going to finish with our last addition reaction. And then when I see you on Thursday, I'm going to then do the elimination reaction, esterification, and polymerization. We should manage to get through all of the rest of organic chemistry in those lessons. Organic chemistry does take time, but I think today us spending a little bit of time getting everyone to practice at each point probably made it a little bit more likely for you to remember how they work. But please remember, you're not going to remember anything if you don't keep practicing this. So at this point, if you think, yay, I got it today, I'm perfectly good, you're not. You're fooling yourself. Okay, so our addition reaction here is hydration. So this is our last one here. Hydration means we're adding in water. Okay, now while I'm just quickly doing this, I want to chat to everybody about master classes. I have recently realized that I very stupidly, I don't even know how it happened, We lost a masterclass. I never did a masterclass on electricity. And it was only when somebody said, where's the video, that I suddenly realized that when you guys went on that weekend off and everybody, well, the week off and everybody took the week off, but I still had a masterclass and I forgot to do it. So there are 2 masterclasses that still need to be made up. At this point, I'm finding that I'm really struggling to keep up with everything. So what I may do with the masterclasses is just the people who've made it get to hear about them, and then you guys will see when they go up online. But at this point, getting everything in, I'm sure you guys can relate to even just attending these lessons at on certain days can be quite a mission to do. So I am still doing all of the masterclasses. They're just by invitation only and for people who've done enough practice on Siyavula. So obviously you guys can all go onto Siyavula, do your practice and then join me, but you got to make sure you do it. Okay, so our addition reaction here being hydration is adding in water, but that's a little bit confusing because we don't actually put in the water directly. What we need to do here is we also, in order for this reaction to occur, need to have an acid catalyst. And there are only 2 acid catalysts that are going to work. So the acid catalysts that you have a choice of are sulfuric acid or phosphoric acid. And you need to make sure that you remember those 2. I find that I always do it with sulfuric acid, but it just is worthwhile remembering that so that you don't have an issue. All right, so from here, when we've got our acid catalyzed, what's going to happen is this water is going to add in. One side will be hydrogen, one side will be hydroxyl. Once again, the rule holds with Mckovnikov. We're going to produce 2 products. The major product is still going to have all 4 carbons. This side has 1 hydrogen, this side has 2. So the hydrogen will go and add to the side that's already got 2. And the hydroxyl group, which is my OH, will go and add to the side that's more substituted. Yeah, remember, obviously, if you've worked out where the more hydrogens go, then you don't have to worry about doing it that way. You figured out which way around they go. So this over here will become my major product. And we can also add in here that the less popular version where we get our minor product is where the H gets stuck here and the OH goes there. Please, there is a line there. And that over there is then your minor product. So both of them do form. The major has much more of it forming than the minor. Okay, so this over here is my minor product. We need to be able to name them. This over here is on carbon 2, so 1, 2, 3, 4. So this is 2-butanol or butan 2-ol. This over here is carbon 1. So this is 1-butanol or butan 1-ol. All right, and usually would only focus on them. How do we know which one is major and which one is minor? Remember, I explained to you just before that we do Mckovnikov addition, and Mckovnikov says that when you add something that's got 2 different groups or it's asymmetrical, the hydrogen will go to the side that's already got more hydrogens, or my version, the hydroxyl group, the more important group, will go to the more substituted carbon. So here you'll notice that the hydrogen went to where there are already more hydrogens, and the hydroxyl group went to the more substituted. So this over here is favorable to occur. What realistically happens here is that the double bond breaks, the electrons in it go and grab a hydrogen added in here, and we have to have a positive ion very temporarily sitting on one of the 2 carbons before the OH minus can get there. And the carbon that has more neighbors is going to be more stable holding that positive charge until the hydroxyl group can arrive and react. That is the full explained reason why you're always going to have the OH on the more substituted carbon. But it also works out that if your hydroxyl, or in the previous case, your halogen atom goes to the more substituted carbon, then your hydrogen's got to be left on the least substituted carbon. All right, So we'll end up producing two products here again. Quick question, does the water have to be in steam and in excess? It's possible. I've never really fussed too much about what form this water's in, as long as you've got an acid catalyst. Obviously, you've got two words that you've just described there. So I'm just going to repeat what they are. Steam and excess. If something is in excess, it means that there's more of it than we need, which according to your chemical equilibrium and Le Chatelier's principle will drive the forward reaction. So if we've got more water, there's a greater certainty that all of it will react, and every little bit of alkene will get turned into alcohol. So that's part of it. Steam is water that is turned into a gas. Now this will work if you don't necessarily have steam, but steam will provide a lot more energy, which means it'll be more likely to favor the reaction happening. So both of those are not essential. You do need, I didn't put it over here, you do need heat, but I don't know if the heat necessarily means that we have to turn our water right the way up to being steam. Okay, so if you've been told that in previous examples, don't stress about putting it in. We usually tend here to examine a little bit more for the needing heat and the fact that you need your acid catalysts specifically named and what the major and minor products are, as opposed to exactly what form the water takes. So if they specifically tell you it's H2O and it's liquid, by all means go with that, but I don't think it's one of those have-tos. All right, okay. Ladies and gentlemen, please can I ask you to take a screenshot of everything that you need? I'm going to stop sharing in just a second. All right. Whew. I hope that that made good sense to you. I know that there's quite a lot of information there. This section is one of those where you need to ideally have repeatedly practiced throughout the lockdown and through the last little while. If you haven't, please use the opportunity from now until you write prelims to go and do a whole bunch of these questions. They're usually right at the beginning of the exam paper. So you typically have your multiple choice. Then you'll have your first question on organic chemistry. You usually have 3 questions on organic chemistry. So these will typically be question number 4 in past papers, but I strongly recommend you go and practice them a lot, because what I've done with you here is just kind of an appetizer. It's not really getting to the meat of any of this, but it's to give you enough information to get started or to remind yourself as to how all the parts fit together. A large number of you, I think, are used to seeing this on paper and as theory, but you've got to actually sit down and practice, or you're not going to be able to do it properly in an exam, especially since they sometimes almost camouflage what they're asking. So I've done really simple examples here where it's very clear what I want you to do, but quite often you'll find that they aren't quite as clear-cut in an exam. So practicing is the only way that you're going to get accomplished and competent at this.